Okay, so there is a rigid body which I've shown in the frame. It is rotating, and there's a point P on the rigid body, and our goal is to find the velocity of this point P in the global frame x0, y0, z0. Okay, and one way to do that is to write a relation between p0 and p1. P1 is the position of point P in frame x1, y1, z1. So if this is the rigid body, and let's say we want to point here, this is x, y, and z coming out, then the point P in the local frame is going to be whatever the length of this is. Okay? So that's P1. Okay? We're trying to keep track of that point P1, say here, P1 with respect to a frame which is fixed to the ground, which does not move. That's x0, y0, z0. So let's say that this point initially is right down there, which means that it's going to be along the x-axis of the frame. So let's say 5 meters. Okay, so this distance is maybe 5 centimeters, but the actual point P with respect to that frame is 5 meters. So let me draw that here. It makes it easier to understand. So this is the body. This is point P. Then P0 would be L. This is capital L. Sorry, my bad. This should be P1. P0 is capital L. Okay, so you've probably done this before when we did the homework, where you try to find how objects move, how the vector moves when you rotate the object. So we start off with this rotation. P0 is R1, P1. Well, when I say P1, I'm really talking about not just, this is really, the P is basically not just the, it's the vector P0. This is a bad notation. I should write. I think we wrote, what's the notation we use for homogeneous transformation? Thing with H. So this is R10, O100, P11. Okay, so this P is this matrix or vector with a 0 appended to it, and that's just a way in which we can represent rotations as well as translation in one compact way, right? That's the homogeneous transformation. Okay, so P0, this dash indicates the 4 by 1 vector I've shown here. So P0 is effectively R10 P1 plus O10. Okay, so we are interested in finding P dot. That's our goal, and the simplest thing you can think of is to differentiate this expression here. So we find the derivative with respect to time. So when you take the derivative of two terms, R times P, we do the product rule. So first we take the derivative of R1 with respect to time, and then keep P1 constant, and then keep R1 constant and take the derivative of P1 with respect to time, plus O1 dot O. Okay, let's do a little bit simplification here. Let's try to express R dot well, let's try to express, let's get rid of P1. Let's put P1 as, well, let's, from here, what we can do is we can write P0 minus O10 is R1. I just move the O10 on the other side, and then I'm going to multiply both sides by R10 transpose. So R10 transpose P0 minus O10 equals R1 transpose R10 P1. But R1 transpose times R10 is the identity matrix. So we've effectively written down a formula for P1 to an aside. Okay, so this P1, let's replace this P1 with the P1 we found from manipulating that equation. So let's write P dot 0 as R10 with the derivative. P1 is R10 transpose P0 minus O10 plus R1 P dot 1 plus O10 dot. Okay, now this thing here is something we found out last class. It was basically the rotation matrix, the skew symmetric matrix associated with rotations. Okay, so we can write that as S omega times all that, but we've seen that if you have A cross B, vector A times vector B, then it is S of A times B. So I'm going to use that fact to write a matrix equation as a vector. So I would have omega cross so this is using A cross B is S of A times B. That is, a cross product can be replaced by the skew symmetric matrix S. So that is the formula I was after. Okay, so a few things about the formula. So the formula gives me P dot 0, which is how P moves with respect to frame OOX0Y0, which is basically the global frame or the fixed frame. Okay, P0, O10 is obvious. O10 is the position of this, which you will know. P0 is the position in global frame. Okay, now we're left with two more things here. P dot 1 and O dot 1 with respect to 0. So O dot 1 with respect to 0 is kind of obvious that it's basically how the origin of that coordinate frame x1, y1, z1 moves with time. Of frame x1, y1, z1 moves with time. And what is kind of tricky is this part, p dot 1. Okay, this is how p moves with respect to frame x1, y1, z1. So that is a part which is most confusing to people. So let me explain what this really means. Okay, so if you have a rigid body and it's moving, and let's say P is this point, P dot 1 means how fast or slow this point is moving with respect to this frame. Okay? So when the body is rotating, P dot 1, which is fixed to this uh, uh, object, is not going to move at all because its distance from this point is fixed and that is not changing with time. Okay? However, if I now make this to be my object and this point, which is this chalk, is moving, so as the body is rotating, this point is moving, let's say up and down like this, but it's always moving along the x-axis, then p dot 1 is going to be not equal to 0. In fact, it's going to be whatever speed this is moving. So let's say that this chalk, which is on this edge, is moving at a rate of 1 meters per second, okay, in this direction, always along the x-axis. So as this moves, this point also moves, then p dot 1 is going to be 1 meters per second. If this point is fixed, it's equal to 0 because as this turns, this point is not moving with respect to this frame which is attached to the moving object. So that's the distinction between p dot 1 and p dot 0. P dot 1 tells you how this point moves with respect to this frame, but p dot 0 tells you how this point moves with respect to the base frame, which is there. So even though this is fixed at a distance, whatever the length is, and does not move, it will have a velocity with respect to the base frame. Okay, so that part I think is most confusing to people. There is a when you took dynamics, there's a section called Coriolis acceleration, Coriolis velocity. We do not teach that in dynamics anymore, and that's where this part actually comes. That's an aside. Okay. Any questions on that? So okay, so here is how to use this formula. Essentially, you'll be given most likely you'll be given the right hand various things in right hand side. You need to interpret them right, put that in the formula, and then solve the problem. So here is an example. So this is a planar disk in the plane x0, y0. Okay, so it's planar and z sticks out of the plane. Okay, so the question is the disk is spinning with constant angular velocity of omega, okay, at time t equals 0 the point P is at a distance x0 along the, let's call that A, along the x axis. So find velocity of point P at time t, so at a generic time. When I say it's spinning with constant angular velocity, it means it's spinning about the z-axis. This is about z0 axis. Okay, so here's how you will do it. You want to find the velocity of P. And when I ask you for the velocity of point P, it generally means I'm asking you to find the velocity of point P with respect to the global frame. So P dot 0 is unknown. That is equal to omega cross P0 minus O10 plus R10 P dot 1 plus O10. Okay, so first of all, as point P moves, the frame also, which is keeping track of P, also rotates with the object. So at a different time, we would have, this is the initial position at a new time, x1, y1, and z1. So point P is right here, and this angle, let's say it's theta. Okay, so what's happening is that the origin is still at the same point. It's not translating. So O1 dot is equal to 0. It does not move, right? The origin is the same point. P dot 1, which is the linear velocity of point P in frame 1, is also equal to 0 because point P is fixed on the disk. If it was not fixed on the disk, it was moving at its own speed. Let's say it was moving this way, then its speed would be whatever the speed is along x1, but that's 0. And then what else? O10 is the position of point where the origin with respect to frame 0, that is also going to be 0 because that does not translate, it doesn't move. Okay, so that simplifies a few things. Okay, so we have to find, so this cancels off, this effectively goes away, this goes away. So we're left with P dot 0 equals omega cross P0. Okay, so let's find omega, let's find P, and we're done. If you like, you can write it as, well, the number of ways to do this. One is, that's simply omega times k. Right? Crossed with the position of P, but you got to keep track of, so position of P is not, initially the position is here, after some time P the position is there. So position of P changes with time. You can see that the position is going to be R10 times P1, which is So R10 is the rotation associated with the disk about the z-axis. So the formula for that is cosine theta, but theta is equal to omega t, just because omega is constant, so you can write omega t is equal to theta. So cosine omega t minus sine omega t sine omega t cosine omega t 0 0. And then P1 is the position of point P in frame 1, which is A0 0. Because it's always going to be along the x-axis, x1 axis, its location is A0 0. So if you do this computation, you should get A cosine omega t, A sine omega t, and 0. Okay, which is what we expect, right? A cosine, A sine, this is just from trig. So then I'm going to put this over here. A cosine omega ti plus A sine omega tj. Let me rewrite that on the next page. So P dot equals omega k cross A cosine omega ti plus A sine omega tj which will be minus omega A sine omega t omega A cosine omega t 0. Okay, there's another way to do this. If you thought that this was hard, if you thought this was, sometimes it's not easy to find omega as omega k, because in this case it's simply a rotation about the k-axis, but sometimes that's not the case, in which case you want to rather use the S formula. So the S formula is this. So here's another way to do it. Another way. Okay, so since we cannot find omega easily if it is rotation about multiple axes, then what I would recommend is writing this as S omega times P0, but S omega is R1 dot transpose times R10 times P0, and so then R1 dot is going to be d dt of whatever we wrote for cosine for R10, so cosine omega t minus sine t okay, so that will come out to be minus sine omega t times omega cosine omega t times omega Okay, so once you get R dot, it's a matter of taking this formula and subbing in the values. So P dot equals R1 dot 0 transpose R10 P0. All these things are known. This is known because we just found it here. R10 I wrote down earlier, and P0 is P0. Yeah, P0 is also known. I wrote it down as A cosine omega t A sine omega t 0, right? This also was derived. So everything here is known. I've reduced down, what I've done is I've written down everything as a matrix, and sometimes that's easier than trying to solve it this way. So it's really up to you how you want to solve it. MATLAB can do both. If there's a function called cross, which can do A cross B. A cross B, the cross is the vector cross product. But if you don't want to do that, you can use matrices using the skew symmetric matrix. Okay, so that is about velocity of a generic point. In this course, we are specifically interested in finding the velocity of some point on the manipulator, right? Because if you want the manipulator to move, it's not only important that the manipulator moves to a certain point. We have an angular velocities of points. Actually, there's another application. So, two applications of one is find Jacobians may be used to find A velocity of points and bodies. So velocities of points and angular velocities of bodies. It can also be used to find the static forces. Okay, this is actually interesting. When you found static forces in statics, you drew a free body diagram, and then using the free body diagram, you found forces. And I think that is a nightmare for many students to draw free body diagram and use visualization to find. So Jacobians actually give you a way of finding the forces without having to draw free body diagram. Okay, and they never teach this because it's slightly more harder than what you want to learn in sophomore class. Okay, so let me motivate this. The position of the end effector So we found AN0, right? Remember, if you go back to this part where we talked about DH, you first put frames, you wrote the DH table, then you found AN0. And AN0 is a function of the link degrees of freedom, so either prismatic or revolute. Prismatic would be thetas, D's, and revolute would be thetas. Okay, so given this transformation, that is the position of the end effector, rotation R, and position ON, in order to find velocities and angular velocity of the end effector link. Okay, Vn0 is the velocity of the end effector. To find that, what we do is it's as simple as taking the derivative of the position, right? So ON0 is the position, and so we find the velocity of that by taking the first derivative. So that's obvious. So what I'm suggesting is, once you do the DH convention, you found the pH table, you wrote AN0, you have this, and that ON0 is going to be a function of Q, that is the various joint angles. Just find the derivative of ON, that thing, the three elements there in the fourth column, and then you have Pn. And if you want to find omega n, it's a little bit more complicated. It is omega n0 equals R dot Okay, so this is how you can do it if I did not tell you anything about the Jacobian. There's no Jacobian here. Jacobian will be denoted by the symbol J. There's no Jacobian here. This is how you would do it if you knew nothing about Jacobians. Find an, find this term which is available here, take its derivative, multiply with transpose. Now what I'm going to do is, I'm going to make your life easy by showing you that you can actually write this as, this is probably the hard way. So the easier way is this. Is we're going to write Vn0 as jv q dot, where q is the degrees of freedom, could be rotation or translation, and omega n0 is j omega q dot. You could write this as Vn0 omega n0 equals jv j omega q dot, where this is the Jacobian. So this vector here on the left side is 6 cross 1, because velocity, there is vx, vy, vz, omega is omega x, omega y, omega z, so that's going to be 3 and 3, 6. Q dot for n link manipulator is going to be n comma 1. So if you have 10 joints, Q is going to be 10, right? Because there are 10 degrees of freedom. And then clearly for j omega to make sense, to have this multiplication to be compatible, you need to have j to be 6 comma n. So when you do 6 times n comma 1, you get 6 cross 1. So what I'm going to do is I'm going to show you how to find jv and j omega. You can write it down. Once you have the DH table, you know it's a prismatic joint or revolute joint, you can write jv, j omega, a formula for that, instead of carrying out this dot. So you see that if you do this way, you'll get the right answer, but it will be very messy. It won't be very compact. This is going to be very compact, and that's why we do it. In general, what happens is when we do later on, when we talk about dynamics, this will really be useful, because then the equations become more compact than using this form. So both of these are harder. So both of these are valid, give the same answer. This is going to be the second one. The Jacobian method is going to be more compact, easier way and more compact. Okay, so I'm going to tell you how to find the Jacobian, and then we'll do a bunch of problems. So as I said, there's a Jacobian associated with the linear velocity, jv, and there's a Jacobian associated with the angular velocity, j omega. Okay. So I'm going to give you a formula for jv and j omega, and I'll motivate this. I'll actually derive this. It's much more intuitive than just giving you the formula. In fact, I think you need to know how it comes, because there are some problems where it's not just blindly putting down the formula, but you got to think about the Jacobians, physically what they mean. So computing check. Okay, computing j omega, we'll do that first. Okay, my goal is today is to finish j omega jv and then let you go. Okay, so the DH convention. So for the DH convention, we have two links like this. zi, zi minus 1, zi minus 2. This is joint I, link I minus 1. Okay, if the ith joint is revolute, okay, so that joint which I showed you, joint I is revolute, then we can write omega I minus 1. So that is basically the angular velocity of link I with respect to I minus 1. So it's the relative velocity of one link with respect to another is simply theta dot times k. So here's the good thing about dx, which is you only have rotations about the j-axis, or sorry, the k-axis, because remember we fixed the z-axis to be along the axis of rotation. So if the ith joint is prismatic, okay, so imagine that this two links, the joint is prismatic, it goes back and forth, it doesn't rotate. Then omega I minus 1 okay, so if the two joints, so omega I minus 1 with respect to I minus 1 comma I is basically giving the relative velocities. So if it's revolute, it is theta dot ik. But if it is prismatic, going up back and forth, there's no rotation with respect to each other, so it's going to be 0. Okay, so we wrote this formula earlier. This was in the last class. We wrote a formula for the end effector. The formula was omega n0 equals omega 0 1 0 plus r1 0 omega so on all the way to so what I'm going to try to do is, instead of writing it as r1 omega 1, I'm going to reuse these expressions to write the formula for these things, right? This is I minus 1 comma I, which means, for example, if you put I equals 1, I get omega 0 0 comma 1. So I need to put I equals 1. So 0 0 comma 1. So that's this. And then if I put I equals 2, I get this thing. And then 3 and so on. Okay. So what happens is, if this is revolute, if this joint, the first joint is revolute, it will be that. If the second joint is revolute, again we put that, but you put I equals, in this case 2. If it is prismatic, you put 0 and so on. So instead of writing it down, we can write it in a very generic way as follows. I'll write it down as rho 1 q1 theta 1 q1 dot k. So q1 is the degree of freedom associated with the link 1. Rho 2, I'll explain what rho 2 and rho 1 mean in a bit, plus rho 3 q3 dot k plus so on till rho n. I'm missing the r's. I should not miss the r's. So r10 rho q2 dot plus till rn minus 10 rho n qn dot k. Okay, where this rho I equals 0 if it's a prismatic joint, and rho r equals 1 if it's a revolute joint. This is just taking care of the fact that some of the joints would be revolute, some of them are prismatic. For revolute joint, I would have theta I, and it will be 0 for prismatic joint. And so what I can do is I can write this as omega n 0, rewrite this expression as rho 1 k, rho 2 k, rho 3 k. I'm again forgetting this. Rho 1, rho 2 k times r1 0 k, rho 3 so on till rho n rn 0 k, and then this is q1 dot, q2 dot, q3 dot, so on till qn dot. So if you look at the formula carefully, this is j omega. In fact, I wrote omega n 0 equals j omega times q dot. So what we've done effectively is we found a formula for j omega. It's very simple. You only need r1 0, r2 0, and so on to find that formula for j omega. You don't need to take any derivatives like I wrote down earlier. So this is a formula for j omega. I'm going to next derive a formula for jv, and we'll be done. And then I'll show the application next time. Okay, next is JV. So what's JV? Well, JV gives me is the relation between V and Q dot, right? So I'm going to write this. This is my formula for Vn. I can write this using a different notation. So this is d. This is the partial. Because there are multiple links, I can write it as that I goes all the way from 1 to n. This is by chain rule. Okay, when you expand this out, you get do n dq1 dq2 and so on till do n dqn. Then you have q1 dot, q2 dot, so on till qn dot. So this term is JV. Or in other words, Vn0 is JVQ dot. Okay, I'm not done yet. I still have to find JV. JV I wrote it down as D DON DQ1, but what is DON DQ1? And so we'll see that